Hi everyone. Today we're going to start talking about modeling with conic sections, and as you notice there are already some typed things on the page in front of you. So while I'm talking for a little bit, if you want to start copying these down, and if you are not done by the time I'm done ready to go on to the next part, just pause the video and write the rest of it down. So basically we're getting started with what the assessments are going to look like. And this model that we're going to do today is very lengthy, but it's not as long as all the problems are going to be. Basically, this one is going to show you a sample of what all of the different types of problems can look like, but your homework problems will not be this long. They will pick one conic. I'm going to show you all of them. So let's talk first of all about a few key pointers you need to know about the modeling and what is important on your assessment. First of all, you're going to be given a real-world scenario, and you get to choose the location of the axes and the coordinates of all your points. So I'll talk about that as we do the first problem so that you have an idea of how to make your workings work best for you and not be too tedious. Second thing is to write sentences in context supporting your workings. That's very, very important, and I will model that as we work through these problems. Thirdly, draw a model for each conic. As you go through and do the conic variations, you need to draw a picture for each one. When you do each conic, at the end you must state the graphing form of the equation and the domain restrictions that go along with it. I will show you a way that you can shorten that domain restriction so you don't have to write it every single time. That'll make your workings a little bit easier. And number 5 is to answer the question in context. Make sure you write those sentences because that's what gives you tick marks that gets you towards excellence. The first question that we're dealing with deals with a satellite dish. Now, you don't have to copy this example down word for word. I'm going to basically summarize below it what you need to know. This is the way that the assessment is going to look. It'll give you a problem like this. It says a satellite dish can be modeled by a variety of conic sections. If a satellite dish is 12 kilometers wide and 2 kilometers deep, find equations to model the dish. So we're going to start with what we consider the easiest one to do. So think about a satellite dish, which is kind of a bowl-shaped object. And if it's 12 kilometers wide and 2 kilometers deep, that looks kind of elliptical. So we're going to start out by modeling the ellipse because it's the easiest. So I'm going to write a sentence stating that and basically talking about what we're dealing with. So I'm going to say the satellite can be modeled with an ellipse. Now, before I go any farther, I'm going to sketch out what I'm thinking of here. So I've got this right here. If it's 12 kilometers wide and 2 kilometers deep, the easiest thing to do is to put the center at 0, 0. So I'm going to go 6 and 6 in each direction here to make my 12 kilometers wide. And then I'm going to go 2 kilometers deep. So this point would be 0, -2. And I'm going to sketch this in. There's my satellite dish. I'm going to put, whoops, I forgot to draw it. The center is 0, 0 with center of 0, 0 and A equal to 6 and B equal to 2. They'd like you to put A and B down for your ellipse as you're writing your equation down. I'm ready to go. I'm ready to write the equation for this one. H and K are 0 and 0, so that means the tops of my fractions are just going to be x squared and y squared. Now, using your formulas page, or looking back at your formulas, remember that A is always the bigger denominator, and A always goes under the variable that it affects. Since A is 6, and 6 is in the x direction, that tells me this is going to be x squared over 36. B is 2, so y squared is over 4, equals 1. So that problem is finished. And now I need to talk about what are called the domain restrictions. Which piece of the ellipse am I dealing with here? I am dealing with an ellipse that goes between -6 and +6 on the x's, and it goes between -2 and 0 on the y's. So that needs to be a part of your answer. All right, that takes care of the first conic. Now we need to talk about how we are going to see if this is a circle. I need to go to a new sheet of paper because I do not have enough room on here to do the circle part, because circles do take a little bit more space. So I'm going to go ahead and draw my picture first so I know what I'm dealing with here. Now the center of my circle is not going to be 0, 0 this time. I am still going to go through these 3 points. because any point with a 0 value anywhere is going to be a lot easier to work with as far as the number crunching is concerned. Okay, so this happens to be part of a circle that looks something like this. So, do you know the radius of this circle yet? The answer is no. But I do know 3 points on the circle, and we did learn how to find the equation of a circle given 3 points. So I'm going to state in a sentence what I'm going to be doing here. It can also be modeled with a circle that passes through the points -6, 0, 0, -2, and 6, 0. So there's basically my statement of what I'm going to do. I'm going to find the equation of this circle that goes through those 3 points. And we're going to do that the way we learned how to do it in Circles Part 2. So first of all, remember that we take the 3 points and we plug them into the generic formula for the circle, which is x squared plus y squared plus dx plus ey plus f equals 0. Do you remember that? Hopefully you do. So we'll start with the -6, 0. So that would be -6 squared plus 0 squared plus d times -6 plus e times 0 plus f equals 0. I need to clean this up. These two together make 36 minus 6d plus f equals 0. Bring this over. -6d plus f equals -36. There's my first equation. All right, do it again with the other two. Just to shorten this video, I'm going to pause and let you finish out these other two and see if you can get the 2 equations. Here are the 3 equations that you should have. Stop for a second and make sure your equations match mine. Now the next step is to put this into the calculator. So the calculator, take a second to do that, and you will get that d equals 0, e equals -16, and f equals -36. So now you're going to have x squared plus y squared minus 16y minus 36 equals 0. There is no d term. So we really only have to complete the square once here. There is no completing the square to be done with the x. So we put together a y squared minus 16y plus blank, putting your 1 blank on the right. All right, so copy the x squared, draw your brackets. This will be -8 and -8. What goes in the bracket? 64. Other side, 64. So we now have x squared plus y minus 8, the quantity squared, equals 100. And there is the equation of my circle. Now, as far as domain restrictions go, are they the same as before? And the answer is yes. So we can put -6 is less than or equal to x is less than or equal to 6. -2 is less than or equal to y is less than or equal to 0. And there's my domain restriction for the circle. The circle is the most involved of the 4 that you have to do. So let's move on to the parabola. So I'm going to talk about how the parabola is going to look first before I write my sentence. And you guys probably should do it this way too. Now, since it goes through these points, 0, -2, 6, 0, -6, 0. Now you could move your parabola up to where the vertex is 0, 0. But you would also have to move the other 2 points up 2 units as well and do it that way. It will work just as easily where it is, and just for consistency, I'm going to keep it the same. So my parabola is going to look something like this. Not a very good drawing, but you get the idea. It can also be modeled with a parabola. Now, what do you call that 0, -2? It's not the center. It is the vertex. With the vertex of 0, -2 that passes through the points 6, 0 and -6, 0. Now, in reality, you don't need both of those points to find the equation. You only need one. So now we have to think about the parabola and what equation it is. This is an opening up parabola. So go back to your formulas and you realize that when you do this one, the one that is squared is x. X minus 0 squared, because this over here is h and k, x minus 0 squared equals 4c. Now, do I know c yet? The answer is no, I don't. So this is 4c bracket y plus 2. There's my equation that I know so far. Okay, so I have 3 variables in here, x, y, and c. I know another x and y. That's the point 6, 0. So I'm going to plug in 6, 0. So I'm going to write 4, 6, 0, showing that I'm plugging that in. I'm going to get 6 minus 0 squared equals 4c bracket 0 plus 2. Now you need to solve for c. So 6 squared is 36. 0 plus 2 is 2 times 4c is 8c. To solve for c, we divide both sides by 8. And we get that c is equal to 4.5. You can do that on your calculator. All right, so now we're ready to write the final equation. It is going to look pretty much like the first line of this problem. And we're going to get x minus 0 squared equals 4 times c. You can put that in your calculator. It happens to be 18. Y plus 2. Or you can just write it as x squared equals 18 y plus 2. Now, you don't have to put both. You just pick one. Now, the satellite dish, in actuality, this is a little dangerous here. I really shouldn't have done this. This is a dotted line because that's not part of the dish. So let me come back and fix that. It just shows that it's parabolic shaped. Is the domain the same? The answer is yes. Negative 6 is less than or equal to x is less than or equal to 6. And negative 2 is less than or equal to y is less than or equal to 0. So there is the domain restriction for the parabola. Okay, now on to the hyperbola. So for the hyperbola, there are 2 cases. The assessment has been seen in 2 different ways. The first way is the way it is already. There is no information about the center at all. And what they assume from this thing, that you can just base A and B on whatever you want it to be. So when they give you no information about the center, you just need to, the easiest way to do it is let A equals 1 and work accordingly. That is the easiest way to do this problem. Otherwise, you could set A to be whatever you want, and then you would solve for the B and find it out. But if A is 1, it makes the math easier. So I'm going to set up the problem the way it's going to look in this case. So we're going to draw a picture first. Here's our 2 points. Here's our lower point. So we're dealing with a hyperbola that does this. There is another one that you can't see that's down here. Now you don't have to draw that in, but I'm giving you a picture of what we're dealing with here. So we have 6, 0 here, 0, negative 2 here, negative 6, 0 over here. So in this case, we know this specific point right here, but that's not the center. That is the vertex. So since they don't tell you where the center is, we're going to just make one up, basically. We're going to put the center right there. And we're going to say that it is 1 unit away from the vertex. That is your A value. So what would the coordinates of that center be? That center would be at 0, negative 3, and we're going to need that. So we're going to write down for the hyperbola model, since we have no center given, we let A equal 1, making the center at 0, negative 3. The vertex is 0, negative 2. Now, what are the other 2 points? They aren't any sort of specific name, but they're points that the curve passes through. And the curve passes through 6, 0 and negative 6, 0. So we're going to use this information to help us build our equation. First of all, think for a minute. Look back at your formulas page if you need to. If it opens in this direction, up and down, does it start with y or does it start with x? The answer is it starts with y. So since the center is 0, negative 3, this will be y plus 3 squared minus x minus 0 squared, or just x squared, it doesn't matter. Remember that a always comes first in a hyperbola, so a will be 1, a squared, is 1 also. The b squared we don't know, so we're going to put a b squared there equals 1. We are going to finish this problem the same way we finished the parabola. We're going to take one of the points that we were given, substitute it in, and solve for b. So we're going to write down the point that we're substituting in, and we're going to get 0 plus 3 squared over 1 minus 6 minus 0 squared over b squared equals 1. Now we need to solve this. 0 plus 3 squared over 1 is 9. We're going to move the 9 to the other side. So this will be negative 36 over b squared equals 1 minus 9. So that'll be negative 8. The easiest way to go from here is to multiply both sides by the b squared to get it off the bottom. So negative 36 equals negative 8b squared. Divide both sides by negative 8, and you end up with 9 over 2. Now, usually the next step would be to take the square root of both sides, but I really don't need to because I need b squared. I don't need b. So I can just put 9 halves. I can just put this 9 halves where the b squared is in the equation. So my equation for this problem would be y plus 3 squared over 1 minus x minus 0 squared over 9 halves, or 4.5, doesn't matter, equals 1. You do not have to put the 0 on top. With the x, you do not have to put the 1 under the y. There are many variations on this problem. So here is the equation for the hyperbola. The domain restrictions are the same as before. So I'm just going to recopy them again. So that is how you do the hyperbola when they don't give you the center. All right, now we're going to look at what happens when they do give you information about the center. Case 2, the center is given. Not necessarily where it is, but information about it is given. And it is usually constructed by two different hyperbolas. Okay, I'm going to say briefly what's going on here. It says one hyperbola has its center 2 units to the right of the dish, and one has its center 2 units left of the dish. So they would give you a sentence like that embedded within the problem, and they will tell you that it is two different hyperbolas. So let's picture this. Let's see what's going on here. We have our graph again. Here's our 6, here's our negative 6, here's our negative 2. So because it's two different hyperbolas, I'm going to draw it in two different colors. I have a hyperbola piece over here, and then I have another hyperbola piece over here. And it tells us that the centers, this one, the one on the right's center, is 2 units to the right. So here's the center of the black hyperbola. So that means this hyperbola looks something like this. It goes up like that, and there is another piece over here. So I'm going to erase this dotted line stuff, and I don't want you to write it down, but I'm trying to show you where the hyperbola is. There's the one hyperbola. The other hyperbola is 2 units to the left. There's its center, and it does the same thing but backwards. There's a hyperbola over here somewhere. So we have two hyperbolas making up this graph. So I'm going to work with the red one first. Let me label my points real quick. 0, negative 2, negative 6, 0, and 6, 0. For the left hyperbola, which I need to specify, the center is what? If it's 2 units to the left, I need to label this point. This is negative 8, 0. What value is A? Remember that A is the distance from the center to the curve, so in this case, A is 2. The hyperbola is horizontal. That's a good thing to put as well, because it tells you which direction it opens. So I now, since it's horizontal, it's going to start with x. So it's x plus 8 squared over, a squared is always first, 4, minus y minus 0 squared over b squared equals 1, just like the other one. We're going to be solving for the b squared. What point are we going to plug in? Be very careful. We're going to plug in this time, not the -6, 0. The vertex kind of gives us a really strange outcome. I messed with that. It's better to plug in the 0, -2 this time because it's not the vertex. You don't want to plug in the vertex. 0, -2. So that gives me 8 squared over 4 minus -2 squared over b squared equals 1. So 64 over 4 is 16. So this is going to move over. So I get -4 over b squared equals -15. Do what we did before. Multiply both sides by b squared. -4 equals -15b squared. B squared equals 4 over 15. So this equation will be x plus 8 squared over 4 minus y minus 0 squared over 4/15 equals 1. Now be careful, your domain restriction is different this time. It doesn't go from -6 to 6. This time it goes from -6 to 0 because I'm only dealing with the red piece of graph. It goes from -6 to 0. The y's don't change. So the y's are -2 to 0. So be very careful with this, that you write it correctly. Now I'm going to start the next one and show you what happens that allows you to jump straight to the end when you do it. And unfortunately I'm going to have to switch pages. For the right hyperbola, the equation is going to be very similar, except that this point is 8, 0 instead of -8, 0. Since it opens right and left also, it's going to be x minus 8 squared over 4, because a is still 2, minus y minus 0 squared over b squared equals 1. Now we're plugging in the point 0, -2 again. I want you to see what happens. When you plug in 0, you're going to get -8 squared over 4 minus -2 squared over b squared equals 1. Take a look at that equation and compare it to the one at the bottom of the page over here. This is 8 squared. The only difference is the 8 squared. That's 8 squared. This is -8 squared. When you square them, you're going to get the same answer. So your b squared value is immediately going to be the same for both hyperbolas. So you can jump to the end and write that down. B squared is equal to 4 over 15. So I can go straight to this equation now and write it as x minus 8, the quantity squared over 4, minus y squared over 4/15 equals 1. Now be careful to write your domain restriction. This one is going to be from 0 to 6, and then -2 to 0 for the y's. And there is your right hyperbola. The next part of the problem will ask you to find specific points. So let me show you what this looks like. This would be like a part B. The dish that we're dealing with has 2 antennas. One antenna is 1.5 kilometers to the left of the deepest point. The second one is 1.5 kilometers to the right of the deepest point. All right, the question also says the poles extend 1 kilometer above the top of the dish, and then it asks you to find the length of the poles with the ellipse model only. All right, so now what we're going to do is we're going to redraw this so we have a model to work with. We've drawn this like 6 times now, so I think we've got it down. All right, it says that there are 2 antennas, 1.5 kilometers to the left of the deepest point, which means it's somewhere over here, and 1.5 kilometers to the right of the deepest point. Now, why did I make them go above the line? Because it says they extend 1 kilometer above the top of the dish. So I want to find the length of each pole. Let's label real quickly. I'm going to blow this up a little bigger. Where's the 1.5? That is this distance right here is 1.5. This distance here is 1. This distance here is what I do not know. So what I'm going to end up doing is taking my model that I came up with for the ellipse. This 1.5 is an x value. So basically, the coordinates of the point right here are 1.5 comma something. And that something is going to be the height of the pole inside the dish. So what I need to do is summarize what I'm going to be doing here. I need to find the y value of the ellipse equation at x equals 1.5 and x equals negative 1.5. This will give the height of the antenna in the dish. So we're now going to rewrite the equation down, which was x squared over 36 plus y squared over 4 equals 1. I am substituting in the point 1.5 comma y, because I don't know what y is. So 1.5 squared over 36 plus y squared over 4 equals 1. Once again, we are solving a problem for a variable within the equation. Now, if you take the 1.5 squared over 36 and move it over, it's going to come out to be negative 0.0625. You will subtract that from the 1, and then you will multiply it by the 4 to get the 4 off the bottom, and you get y squared equals 3.75. So y is going to be, the y value there is going to be plus or minus the square root of 3.75. The y value there happens to be negative 1.9365. Now, the y value is really the point on the curve down there. The point on the curve right here. But I want to know that height. So I need to be a little more specific here. The height of the antenna equals 1.9365 kilometers plus the 1 kilometer outside the dish. So the height of the antenna on the right hand side will be 2.9365 kilometers. Now that is the right hand antenna. Will the left hand antenna be the same height? The answer is yes, and you need to say that. The height of the left antenna will be the same, so the height of both will each be 2.9365 kilometers, and it's done. All right, that's the end of this lesson. The assignment for this in the Griffith book is going to be section 1.10, which is on page 26. Just pick one of the questions. Pick 1, 2, or 3. In the Delta book, it is section 1.07, which is on page 29. And pick any problem that you want to do. Any couple of problems would be good. All right, we're getting down to the end. We're about ready to start the practice task. Please work diligently on this, and please ask if you have any questions.